good afternoon. My name is Qing, and today I'm going to talk about semi-supervised learning. I'm from ETH Zurich. Semi-supervised learning aims to learn a better model by using additional unlabeled data. In a typical setup, we have a very limited amount of labeled data, but additionally, we have access to a large amount of unlabeled data. We assume that these two are drawn from the same distribution. But that sampling from the same distribution means identical empirical distribution. Let's first take a look at the 6 points. Can you guess what is the underlying distribution? Well, it's actually quite hard because there are simply too few examples. And in fact, it's a 2-moon. So take a look at the 2-moon again. We sampled labeled and unlabeled data from the same distribution. The large number of unlabeled data can well describe the underlying distribution. However, the limited amount of labeled data can hardly describe the 2-moon. By applying kernel density estimation on x-axis, we can better see this considerable and large empirical distribution mismatch. Most current methods assume that labeled and unlabeled data are identically distributed. However, in practice, this assumption can be violated because of the empirical distribution mismatch. So let's take a look at the pseudo-label method. We learn a classifier from the 6 labeled points here, and iteratively assign pseudo-labels to the unlabeled data. However, the pseudo-label predictions here are biased. But why? This is because the model overfits to the biased empirical distribution, which leads to the biased prediction. The limited amount of label samples leads to an empirical distribution that deviates from the true underlying distribution. And as a consequence, a model trained from the labeled data is unlikely to generalize well on the unlabeled data. To heal the empirical distribution mismatch, we propose to use off-the-shelf alignment techniques from domain adaptation. The network contains 2 branches. The classification branch classifies the labeled data and calculates the classification loss. In the additional branch, we treat labeled and unlabeled data as 2 different domains and make use of discriminator to enforce the feature extractor to generate well-aligned features. The diversity training is implemented by using gradient reverse layer, and the key idea is similar to again. But there's one potential issue. Too few labeled data leads to unstable optimization because we don't have enough distribution support. So how should we deal with it? One solution would be data augmentation. So in order to reinforce the alignment inspired by mix-up, we propose to use cross-set sample augmentation. We randomly sample a labeled image and an unlabeled image along with an interpolation factor between 0 and 1. We generate new training samples by interpolating between them. And in addition, we make use of the pseudo-label for the label interpolation. The benefits of the proposed augmentation are twofold. First of all, by interpolation, we can generate as many pseudo-samples as we want, and this makes the training data set a lot larger, thus leads to more stable training. And secondly, the Euclidean generalized energy distance between the empirical distribution of the pseudo and unlabeled samples is smaller than or equal to that of labeled and unlabeled samples. We actually have a proof. Please refer to the proposition 2 in the paper. Let's take a look at the final proposed model. On the right side, in addition to the classification branch, we have a discriminator to distinguish labeled and unlabeled samples. Then, for each mini batch, we use a cross-set sample augmentation strategy to generate and interpolate samples and labels, and use them as training data to train our AdaNet. We perform ablation study on CIFAR-10, and we include a baseline which is trained only with labeled data. We observe that both the distribution alignment and cross-set sample augmentation are important for improving performance. We further compare our AdaNet with recently proposed methods on several benchmark datasets, and AdaNet achieves state-of-the-art results on CIFAR-10 and SVHN using the convolutional backbone, and also on the large-scale ImageNet dataset using ResNet 18. So to sum up, empirical distribution mismatch is an important but often overlooked problem in semi-supervised learning. Our code is available online, and thank you for your attention.